Welcome back to the next video, everybody. Today we're going to be looking at some specific deformation conditions given by some specific determinant conditions on Galois representations. This will be a quick one today. We're going to keep the usual notation from previous videos. So we'll take a coefficient ring lambda. A will be a coefficient lambda algebra. V of rho, which we'll also call V, which will be a to the n, is going to be a free A module of rank n with a continuous pi action induced by rho, where rho is just some representation of pi with representation space V, and pi is a profinite group. Okay, so let's let delta from pi to lambda cross be a continuous homomorphism. We're going to say V has determinant delta if the action of pi on the wedge product to the nth power of V is given via the continuous homomorphism, which I'll call delta sub A. It'll be the composition pi to lambda cross, which is just delta, with lambda cross to A cross, where the latter map comes from the lambda algebra structure of A passed to the groups of units. Okay. In other words, the action is G of W equals delta A of G dot W for G in pi and W in wedge to the n of V. Okay. So we're going to keep determinant delta in quotes though, because technically, if you look at what's happening here, the actual determinant of rho has values in a potentially different ring than delta does. Okay. But in some sense, what we're doing here is we're assigning to a representation the determinant delta. Okay. We're also going to note, and this is just an easy check, if rho prime is a deformation of rho and rho prime has determinant delta, then so does rho. That's an easy check. Okay. So is fixed determinant a deformation condition? That's the main question of this talk today. So let's let rho bar be the underlying residual representation attached to rho, so that rho bar also has determinant delta by the above. Consider the property cal D defined by imposing the condition on a homomorphism rho from pi to GLN of A that it be of determinant delta. So proposition 20, the above condition D actually is a deformation condition in the sense of this chapter. So we have a universal deformation ring. Probably we can describe it explicitly as well. But remember, for the full deformation problem, we have that the tangent space is isomorphic to the cohomology group H1 of pi and AB. The question is, for this deformation condition, what is the subgroup of that cohomology group corresponding to the tangent space? Okay, and here it is. You can describe it explicitly very easily. H1 sub D of pi and AB, which is the subgroup of the cohomology group corresponding to the fixed determinant or determinant delta condition, is nothing but H1 of pi n circle AV, where n circle AV is the sub A module of the trace zero endomorphisms. Okay, so determinant delta corresponds to trace zero endomorphisms in cohomology. Also, the sub A module n circle AV is stable under the action of pi. Thank goodness. Okay, so for a proof of this, it's pretty run of the mill. You can see CSS page 291. Okay, what is the universal deformation ring? Given an absolutely irreducible residual representation, rho bar of determinant delta, if R is its universal lambda algebra deformation ring, and rho u from pi to GLN of R is the universal deformation, we can certainly describe R sub cal D, the quotient lambda algebra of R, universal for deformations of rho bar, which are of determinant delta. We can describe this elegantly. Let's let delta u from pi to R cross denote the determinant of rho u, and we'll let delta sub R denote the composition of delta with the natural structural homomorphism u from lambda cross to R cross. So again, delta R is just the composition, pi to lambda cross to R cross, it's a u composed delta. So what is the universal deformation ring of the deformation condition cal D? It's R sub cal D, and it's always, remember, a quotient of R. So it's R mod I. What is the ideal I? I is the ideal generated by the elements delta sub R of G minus delta U of G, which are in R. Okay. For all G and pi, or you don't even really need to check this. For all G and pi, you can just check it for a system of topological generators G of pi. Okay. So starting next video, we'll look at some more things that turn out to be deformation conditions, which will be crucial for us. So we'll look at ordinariness and flatness. So I'll see you then. Thanks for watching.